Imagine for a second that you are putting together a team to manage this massive, like, 30-year retirement fund.
Okay, high stakes.
Right, super high stakes. And you want the best of the best, so you bring in this absolute hotshot day trader. I mean, they look at the morning ticker, they spot these tiny micro trends, and they can tell you exactly what a stock is going to do by 4:00 p.m. with just uncanny accuracy.
Oh, sure. But then you sit them down and ask, well, how will the structural economic shifts of the next 3 decades affect our portfolio?
Like,
And suddenly,
predictive power just evaporates.
totally.
Because betting on tomorrow's momentum is, a fundamentally different discipline than understanding decades of deep structural change.
You're asking a short-term pattern matcher to suddenly become a long-term macroeconomic visionary.
Right, which just doesn't work.
And that tension, that exact mismatch, is the core of what we are unpacking today. Welcome to the Deep Dive.
Glad to be here. We are talking directly to you today, specifically to you and your engineering team, if you're in the trenches, building next-generation, data-driven climate emulators.
Yeah, the ACE-style models.
Right, atmosphere climate emulators. Doing those multi-decade rollouts that are forced by sea surface temperatures. Because you've undoubtedly got a stack of recent, incredibly high-profile research on your desk right now.
Papers making massive claims.
Oh, massive. About how artificial intelligence and machine learning are just completely revolutionizing atmospheric forecasting.
And honestly, the hype is deafening right now. I mean, we are looking at the performance of models like GraphCast, Pangu Weather, and Fuxi.
Which are doing incredible things, to be fair.
Absolutely incredible things. But our mission today is to read this literature through the highly skeptical lens of a climate modeler.
Right. We need to aggressively filter what these breakthroughs actually mean for a multi-decade climate emulator as opposed to just a short-term weather forecast model.
Because the broader conversation out there is sliding between these two use cases all the time.
Without flagging it at all.
Right, without flagging the fundamental architectural differences. So, to set the baseline here, current leading AI models are trained primarily on historical data sets.
Specifically the ERA5 reanalysis, right?
Yeah, exactly, which spans roughly 1979 to 2017. And they're trained with a very specific objective function.
Which is to minimize the mean squared error in, like, 6-hour weather forecasts.
Exactly. And at that specific task, they're consistently beating traditional physics-based numerical weather prediction models on all the standard metrics.
Which is why the hype is so loud. But building a multi-decade climate emulator requires, well, entirely different physics and mathematics than a 6-hour weather forecast.
Totally. And the primary hurdle we encounter here is what we can call the extrapolation trap.
The extrapolation trap.
Yeah. If you are building a climate emulator projecting into a warming world, the fundamental question your architecture has to answer is, well, what happens when your model encounters atmospheric conditions it has literally never seen before?
Because the world is getting warmer.
Yeah.
So we're going to see things that aren't in the 1979 to 2017 data.
Right. And researchers recently set up this brilliant stress test for this exact problem. They took the leading AI models and evaluated them against the gold standard physics-based model.
The European Center's HRES model.
Right, but they bypassed average days completely. They stress tested them specifically on record-breaking extremes.
Oh, wow.
Yeah, the unprecedented heat waves, cold snaps, and windstorms of 2020 and 2018, events that just shattered previous historical boundaries.
That was like the ultimate out-of-distribution test.
Exactly. And the findings present a really significant warning sign for anyone building an emulator right now. The AI models systematically underpredict both the intensity and the frequency of unprecedented extremes.
And the forecast bias doesn't randomly distribute either, right? I mean, the error grows almost linearly with what the paper calls the record exceedance.
Yeah, record exceedance, which essentially measures the margin by which a new extreme beats the old historical maximum.
Okay, so
if a heat wave is merely like a fraction of a degree hotter than anything in the training data, the AI misses the peak by a small margin.
right, it's barely outside its comfort zone.
But if the real-world event is a massive, totally unprecedented heat dome that shatters the old record by, say, 5 degrees...
The AI misses it by a massive margin.
Exactly. It behaves mathematically as though there's this implicit soft cap built into its predictions.
A soft cap anchored to the most extreme observations it was exposed to in the 20th century.
Which traces back to the reality that machine learning models are fundamentally interpolators.
Right. They draw incredibly complex, multi-dimensional lines between existing data points.
But they fail when the training distribution lacks support in the feature space.
Okay, pause for a second. What does lacking support in the feature space actually look like under the hood of one of these models?
Right, okay. So think of the feature space as a vast, multi-dimensional map of every weather condition the AI has ever studied.
Okay.
The support is the actual data points plotted on that map.
The historical weather events.
Right. So if the AI is trying to predict a 2050s heat wave, it is searching its map for similar conditions so it can weigh its output.
Yeah.
But the area of the map representing those new extreme temperatures,
Completely blank.
it's totally blank. There are no data points. And because the model optimizes for minimizing errors based on what it actually knows, it naturally pulls its prediction back toward the clusters of data it has seen before.
It regresses toward the historical mean.
Exactly.
Wait, I'm stuck on something here, though. Because these models are famously excellent at finding hidden patterns in the data, right?
They are.
They can pick up on incredibly subtle atmospheric dynamics. So if they understand the underlying momentum of weather system, why couldn't they just mathematically infer a gray swan event? Like, why is this a hard boundary?
That's a great question. It's because inferring a pattern inside a known data set is interpolation.
Okay.
But projecting a new state outside that data set is extrapolation. And pure machine learning architectures, they just lack the fundamental physical laws required to do that accurately.
Oh, because they don't actually know why the weather's happening.
Exactly. Physics-based models, like HRES, actually outperform the AI on these unprecedented extremes because they don't have that soft cap. They run on the fundamental equations of thermodynamics and fluid dynamics.
Like the Clausius-Clapeyron relation.
Yes, exactly. Which dictates how much water vapor the atmosphere can hold as it warms.
Right.
That equation holds true regardless of whether that specific temperature has ever been reached on Earth before.
Because it's a physical law.
Exactly. The physics extrapolate natively because they define the rules of the system. But the AI only knows the outputs of the system it's previously observed.
So as an emulator builder who is relying on pure ML, trained on historical reanalysis, you are basically designing a model that will actively resist predicting the true severity of 21st century crises.
Yep, it will constantly pull the 2050s back into the 1990s.
Wow.
That is a huge problem. And connecting that soft cap to the bigger picture is where this becomes an existential issue for emulator projects.
Because for a short-term weather model, an extreme event is just a rare anomaly. I mean, missing the peak of a once-in-a-decade storm is a bad forecast week, sure.
But for a multi-decade climate emulator forced by warming sea surface temperatures, unprecedented extremes are the baseline reality.
Right.
If your emulator has this implicit soft cap baked into its weights, it systematically blinds us to the future climate.
And it's one thing to cap intensity on a singular, severe day, but climate emulators aren't just looking for one bad day. They are tracking decades of compounding momentum.
Exactly.
So if the model's architecture caps intensity, how does it handle the slow burn of long-term duration? Like, how does an architecture that is optimized for 6-hour steps handle a 30-year mathematical marathon?
This is where we see a really fascinating dichotomy in the literature when we look at how AI climate models handle long-term atmospheric dynamics.
Because they aren't bad at everything, right?
No, not at all. On one side, we have a stunning success. AI models simulate subtle, fast dynamical processes remarkably well.
Okay, like what?
Well, they easily capture the complex interaction between equatorward propagating transient waves and the mean jet stream winds.
Which is genuinely impressive because nobody explicitly coded wave mean flow interactions into the neural network.
Right. The model just magically inferred these really complex physics purely by trying to minimize the mean squared error on 6-hour weather forecasts.
It basically learned the fast dynamics just by watching the frames of the movie change over and over.
It is a massive triumph of data-driven learning. But, and here's the kicker, the corresponding failure is absolutely critical for emulator design.
Let me guess. It can't do the slow stuff.
It cannot do the slow stuff. AI models struggle profoundly to reproduce slow, low-frequency climate variability.
Like the quasi-biennial oscillation.
Yes, the QBO, as well as the poleward migration of zonal wind features, which we call annular motes.
Let's actually define the QBO for a moment, just to be clear. It's this massive, slow descent of alternating easterly and westerly wind regimes down through the tropical stratosphere, right?
Right, and it takes over 2 years to complete a single cycle.
So it's like this fundamental metronome of the global climate.
Exactly, and it results from the cumulative integration of thousands of tiny, fast weather variations pushing up from the troposphere over long periods.
But the AI can't capture it.
No. The AI fails to produce a smooth decadal cycle here. Instead, it generates this intermittent, physically incoherent behavior.
It's like, imagine a musician who possesses absolute perfect pitch,
Mhm.
right? You play a single complex chord, which is our 6-hour forecast, and they can recreate it flawlessly on the piano,
Great analogy, yeah.
but they have zero sense of rhythm for an overarching symphony. If you ask them to play an hour-long piece, they just lose the beat entirely.
Exactly. You cannot just stitch together 10,000 6-hour weather forecasts and call it a climate.
Because the subtle errors in hour 6, which the model deems mathematically acceptable,
Become massive structural deviations by year 6. The song just turns into noise.
so why does it lose the rhythm, structurally speaking?
The structural reason it loses the rhythm basically comes down to the loss function.
Oh.
Right, because a weather model's loss function does not penalize the AI for missing the QBO. If the forecast horizon ends in 10 days, messing up a 2-year stratospheric wind cycle does not impact the immediate mean squared error.
Because it's not looking that far ahead anyway.
Exactly. But a multi-decade climate emulator relies entirely on that low-frequency variability. The slow accumulation of those wave-mean flow interactions dictates decadal climate shifts.
So if the emulator nails the 6-hour weather, but fails the multi-decadal integration.
The 30-year rollout becomes structurally useless.
Wow. Okay, so if the purely data-driven approach is capping our extremes and losing the decadal rhythm, the obvious pivot for an engineering team is to just lean entirely on traditional physics models.
Right. Just use numerical weather prediction mechanics for the climate rollouts.
Yeah, but that assumes those physics models are an infallible ground truth, which, as we know, is a massive and increasingly dangerous assumption.
Extremely dangerous. Traditional models are facing their own massive crisis of confidence right now regarding what we call the standard approach of climate science.
And that standard approach relies on a core assumption called large-scale determinism, or LSD.
Right, which is the foundational bedrock of how traditional climate physics models actually work.
Because traditional global models don't have the computational power to simulate every individual cloud or localized thunderstorm on Earth, right?
Exactly, they just can't see them. So they use equations called parameterizations.
Which are basically educated guesses.
Yeah, they guess what the small-scale physical processes are doing based on the state of the large-scale atmospheric environment around them.
It assumes this strict separation of scales, where energy just flows predictably from the big picture down to the small details.
Right, so if the large-scale grid shows specific temperature and humidity profiles, the parameterization decides, well, a certain amount of deep moist convection must be happening inside that grid.
But the growing issue is that this assumption is cracking under the pressure of real-world observations as the planet warms.
It's totally cracking. Discrepancies are just piling up at regional scales. The real world is showing us atmospheric signals that the physics-based models completely missed.
Like the unexpected drying trends in South Africa.
Yes, and we're seeing an unanticipated strengthening of the North Atlantic jet in the winter. Plus, we are tracking massive errors in how models predict sea surface temperature patterns in the tropical Pacific.
Right, the actual ocean is warming more in the west, but the models confidently predicted it would warm more in the east.
Which is a huge miss.
And the breakdown here often comes down to scale coupling, doesn't it? Like small-scale events don't just passively respond to the big picture. They actively push back and alter the macro environment.
Exactly. And deep moist convection is the prime offender here. Small-scale convective instabilities, which the traditional models just parameterize away using large-scale determinism.
Because they assume they don't matter that much to the big picture.
Right. But they are actually capable of destabilizing massive tropical circulations. The small scales actually drive the large scales.
So traditional models struggle deeply with this scale coupling.
They do. And they also struggle with component coupling, which is how the atmosphere interacts with the ocean at highly localized resolutions.
Which creates a really profound dilemma for anyone building an AI climate emulator today. Because you might assume you could avoid the pure ML extrapolation problem by just training your AI heavily on reanalysis data, like ERA5.
Because you think it represents the historical ground truth.
Right, but reanalysis data isn't just pure raw observation.
No, not at all.
I mean, we don't have thermometers in every cubic meter of the atmosphere. Reanalysis is heavily processed. It is an assimilation of raw sensor data fed through a legacy traditional physics model to fill in all the gaps.
Precisely. Operational ML forecasting systems today are inherently hybrid systems because they depend on the physics-based models used to create their training reanalysis.
So an AI trained on ERA5 will invisibly inherit all the limitations of large-scale determinism.
It bakes the tropical Pacific temperature biases directly into its neural network. It inherits the failure to capture scale coupling. Everything.
So we are essentially caught between two highly flawed paradigms.
Basically, yeah.
The physics models are failing at regional coupling because of built-in assumptions about how big scales dictate small scales.
And the purely data-driven AI models lack the thermodynamic constraints to predict any extreme they haven't explicitly seen in their training data.
We're just trading a physics limitation for a data limitation.
But identifying the hard boundaries of that space is exactly how you build a better emulator. You have to understand the specific failure modes of your tools.
Right.
Abandoning physics-based numerical weather prediction would severely damage our scientific capability.
Because it's explainable.
Exactly. When a traditional physics model predicts the wrong Pacific warming pattern, scientists can open up the equations, interrogate the parameterizations, and figure out the mechanical failure.
But when a pure ML model fails to predict a heat dome,
It is just a black box of billions of weights reacting to a lack of data. You learn absolutely nothing about the physical climate system from that failure.
so the goal for an ACE-style emulator isn't to pick a side between AI and traditional physics.
No, the entire architectural challenge is hybridization.
Hybridization.
Yeah. The frontier is using AI to augment the physics, or using physics to constrain the AI.
Like how researchers are currently exploring how machine learning can replace specific, computationally heavy parameterizations within a physics model.
Right, which allows it to run faster without losing those physical constraints.
And conversely, teams are running incredible expensive kilometer-scale global physical simulations,
Which actually have the resolution to simulate small-scale clouds instead of just guessing at them.
and then using that specific output to teach an AI about scale coupling.
Exactly. That's where the magic happens.
Okay, let's pull all of this together for the listener. If you were designing the architecture for a next-generation climate emulator conducting multi-decade rollouts based on sea surface temperatures, here is your synthesis from the bleeding edge of the literature.
Take notes.
Point 1. Do not be fooled by benchmark weather scores. An AI model that minimizes mean squared error for a 6-hour forecast has no inherent concept of multi-decade climate stability.
Perfect pitch does not equal rhythm.
Exactly. And stitching together short-term forecasts destroys the slow variables like the QBO.
Point 2. Audit your architecture for the soft cap on extremes.
Right.
Pure machine learning interpolates. It does not natively extrapolate. If your emulator relies solely on historical data, it will systematically underpredict the gray swans of the 2050s.
And that bias grows linearly the further the climate pushes past the historical training data.
Yep.
And point 3, understand that the standard physics models and the reanalysis datasets generated by them have profound built-in blind spots regarding regional scale coupling.
So relying on them as a flawless baseline will just bake their conceptual errors regarding large-scale determinism straight into your neural network.
You have to design a system that mitigates both the AI's data limits and the physics model's scale limits.
It requires an incredible amount of discipline to not just chase the daily hype of an AI beating a weather benchmark.
Because emulators are a fundamentally different science.
Totally different.
So I want to leave you with a final, forward-looking thought to debate with your engineering team. The literature frequently mentions data augmentation as a potential fix for the AI's inability to extrapolate.
Right, adding more data.
But if AI models hit a brick wall because they can only learn from the historical weather we have actually experienced, and the physical world hasn't yet experienced the unprecedented climate of the 2050s, what if the future of AI climate emulators involves moving away from real-world observations?
Oh, generating the extremes synthetically.
Exactly.
Yeah.
What if, to teach an AI how to mathematically extrapolate outside its feature space, we have to train it entirely inside synthetic, hyper-extreme physical simulations that haven't even happened yet?
That's a wild thought.
Are we moving toward an era where AI learns the climate from our mathematical imagination of it rather than the physical reality? And because going back to our day trader, if you want that brilliant day trader to successfully manage a 30-year fund, you might just have to invent a few virtual stock market crashes to teach them how to survive the real one.